All right, so let's look at example 6. It says differentiating the function g of t equals negative 7 all over 2t minus 3 quantity squared. So when you look at this function, a lot of people would think, great, now I have to use the quotient rule. But the quotient rule is not the best way of doing this. How do I know I shouldn't use the quotient rule? Don't use the quotient rule. I'm writing this down. Don't use the quotient rule if it is just a constant on top. So what I'm saying here is, look, negative 7 is just a constant. It's just a number. So how do I want to do this? Well, what I want to do is I want to rewrite g of t as, and what I'm going to do is, this is 2t minus 3 quantity squared on bottom. What would happen if I brought that up to the top? Well, this would be negative 7 times 2t minus 3 raised to the negative second power, and hopefully you agree with that, okay? All I did was move it to the numerator, which makes the power negative. So now I can find the derivative of this function using the general power rule instead of having to use the quotient rule. So what would it be? Well, constant multiple, negative 7 stays there. What do? You drop the power, keep the inside the same, power minus 1, but then you have to remember to multiply times the derivative of the inside. So let me do that again. You're going to drop the power, that would be the negative 2. Inside stays the same, so that's the 2t minus 3, power minus 1. Negative 2 minus 1 is negative 3. And then we have to remember to multiply times the derivative of the inside. Okay? So let's clean this up a little bit. The derivative of 2t minus 3 would simply be a 2, wouldn't it? Okay? And I'm going to clean this up. So now I have a negative 7 times a negative 2, which would be 14, times a 2, which would be 28. And then I have the 2t minus 3 to the negative 3. I'm going to throw that into the denominator. So what am I getting? What am I getting? I would get g prime of t equals, again, 7 times 2 is 14 times 2 was a positive 28, all over 2t minus 3 quantity cubed. So that should be your final answer there, 28 over 2t minus 3 quantity cubed. Notice how much easier that was than the power rule, than the quotient rule on that problem. So using the power rule with a negative exponent is much, much simpler only when you have a constant on top. All right, let's keep on going. Let's look at number 7. It says, find the derivative of x squared times the square root of 1 minus x squared. I love this problem. Great test problem. When we did product rules before, several of the product rule examples we did, you actually didn't need to use the product rule. You could have just FOILed them out. Well, this one, you don't have that option. You don't have the luxury of being able to FOIL it out because you can't combine x squared underneath the radical unless you know a lot of different math, but I don't think you should do it that way. Okay, so what am I looking at? I'm looking at a product rule, right? And so what's the derivative going to be? The derivative is going to be, well, let's figure this out. I'm going to break this down for you so you can really see this. I'm going to call this the first function, and I'll call this the second function. We're going to have to do some work to find the derivative of the second function, and that's perfectly fine. So let's go ahead and remember what we do for a product rule. You do your first function, which is x squared. You need the derivative of the first function. Well, the derivative of x squared is simply 2x. Let's look at our second function. Our second function is the square root of 1 minus x squared, or the way that we probably want to look at it is 1 minus x squared raised to the 1/2 because we have to find the derivative, right? So the derivative of that would be, okay, now we have to use the chain rule. So this would be 1/2 times, drop the power, keep the inside the same, so that's 1 minus x squared to the power minus 1. 1/2 minus 1 would be negative 1/2, but then remember you have to multiply times the derivative of the inside. Well, the derivative of 1 minus x squared would be negative 2x. Let's do a whole bunch of simplification here. So I see a 2 on bottom and a 2 on top. Those are going to simplify. The negative doesn't go away, so I'm going to have a negative x on top. and then I have a negative exponent here of a negative 1/2, I'm going to throw that into the denominator, and I'm going to change it to a radical all in one term. So it looks like I have the derivative of the second function simplified is negative x all over the square root of 1 minus x squared. Negative x all over the square root of 1 minus x squared. Okay? So what do I do from here? Now I need to use the product rule. Remember, the product rule says it's the first times the derivative of the second plus the second times the derivative of the first. Or if you're looking at my page right now, first times the derivative of the second plus the second times the derivative of the first. We do that little cross multiplication type thing because of the way that I organized it. So the first was x squared. Derivative of the second is negative x over the square root of 1 minus x squared, plus the second, which was the square root of 1 minus x squared, times the derivative of the first, and the derivative of the first was simply 2x. So I'm going to clean this up a little bit. X squared times negative x is negative x cubed all over the square root of 1 minus x squared, plus we have a 2x times the square root of 1 minus x squared. Okay? So personally, I would be fine with that as is, but what's going to happen is in the textbook, when they have two terms like this, they want to combine it under a single denominator. So what would we have to do to get a single denominator? We'd have to get a common denominator by multiplying the second term by square root of 1 minus x squared over 1 minus x, square root of 1 minus x squared. All right, get a common denominator. And I want you to notice what would happen. So here we would have negative x cubed over the square root of 1 minus x squared. We would have plus 2x, and then when I multiply the square root of 1 minus x squared times square root of 1 minus x squared, I would get simply 1 minus x squared, because the square root and the square cancel, right? And this is over the square root of 1 minus x squared. Okay, let's keep on going. So this would be, because they have a common denominator, I could combine them. I would add the numerator, so this would be negative x cubed, and what I'm going to do is I'm going to distribute that 2x through. So 2x times 1 is plus 2x. And then I have the 2x times the negative x squared, which would be minus 2x cubed. This is all over the square root of 1 minus x squared. Combining like terms, we have a negative x cubed and a minus 2x cubed. I'm ending up with negative 3x cubed plus 2x all over the square root of 1 minus x squared. So the only thing that you're going to see different on the book, if you're looking at the book, is they notice in the top you could factor out an x in the numerator. And so they factored out that x in the numerator, and they actually have x times negative 3x squared plus 2. No need to do that. This is perfectly fine. Again, quite honestly, I would have been fine with your answer in the underlined purple form right there. Okay, so that was a nice one where we had to simplify with a derivative using the product rule. What about using the quotient rule? So let's look at this next one here. So it says find the derivative of f of x equals x over the cube root of x squared plus 4. So here I'm going to call the function low, and here I'm going to call the function high. Yes, we could technically bring the denominator up to the numerator, make it a negative power, and then use the product rule, but that's truly not much different at all than using the quotient rule as is. So let's use the quotient rule. Let's look at our low function. Our low function is the cube root of x squared plus 4. Or the way that I really want to look at that is x squared plus 4 raised to the 1/3 power. So if we want to find the derivative of the low function, what do? I use the chain rule. Drop the power, keep the inside the same, power minus 1 times the derivative of the inside. So let's do that. Drop the power would be 1/3. Inside stays the same. That's the x squared plus 4. The power minus 1, so 1/3 minus 1 is negative 2/3. And then we need to multiply that times the derivative of the inside, which would be the derivative of x squared plus 4. We need to do some simplification here. What's the derivative of x squared plus 4? Well, that's simply 2x. So now I need to look, what would be left on top? It looks like we have a 1 and a 2x, so a 2x is on top. On bottom, what do we have? It looks like we have a 3, and then this was x squared plus 4 to the negative 2/3. I'm going to bring that into the denominator and change it back to radical form. So when I do that, I would have a 3. The radical would be a cube root of, and then it's x squared plus 4 quantity squared. Okay, this is going to be a mess, and it's going to be a mess quick, but we can deal with it. We'll figure it out. All right. What's our high function? Our high function in this case is x, thank goodness, because the derivative of the high function is simply just a 1. So what's our rule again to find f prime of x? The quotient rule is low d high minus high d low over what's below squared. This is going to be a mess, just bear with me. Again, it's low times the derivative of the high plus the high times the derivative of the low. Sorry, minus the high times the derivative of the low over what's below squared. So let's plug that in. Low, the low function was the cube root of x squared plus 4. Derivative of the high was simply a 1. Minus the high function. The high function, x, times the derivative of the low. That's 2x all over 3 times the cube root of x squared plus 4 quantity squared. And then we have all of that over the bottom squared, which is the cube root of x squared plus 4. That squared, so it doesn't matter if we put the square on the outside like this, or if we put the square on the inside like it is above. I'm just going to make it look the same as the inside as it is above. Okay? So I'm just going to clean this up a little bit. I see an x here and a 2x here. So what do I have? I have the cube root of x squared plus 4 minus, it would be a 2x squared all over 3 times the cube root of x squared plus 4 quantity squared, all over the cube root of x squared plus 4 quantity squared. Remember, if you have, I don't know if you know how to factor very well. That's what they do in the book, but a lot of students mess it up when you do the factoring. A lot of students are better at getting common denominators than they are factoring. So what I'm going to do is multiply, when you have a fraction over a fraction, you just multiply everything by the denominator. So what I'm going to do here, let me go ahead and erase this equal sign. That's a little too close. I'm going to multiply everything times this denominator. So I'm going to multiply every term in the numerator and denominator times 3 times the cube root of x squared plus 4 quantity squared. Everywhere. 3 times the cube root of x squared plus 4 quantity squared. And 3 times the cube root of x squared plus 4 quantity squared. Now, why do we do that? Because a lot of simplification is going to happen. For instance, when we look at the first term, we have the cube root of x plus 4 quantity squared, and then we have the cube root of x squared plus 4. So that would be the cube root of x squared plus 4 quantity cubed. So the cube root and the cube would actually simplify, and this entire thing right here would end up being 3 times x squared plus 4. The radicals and the powers would simplify. In the second term, we would have those 3 times the cube root of x squared x squared plus 4 quantity squareds simplify, and then in the denominator we would left with it's that radical squared times that radical squared, so it'd be that radical raised to the 4th power. So what are we ending up with here? Well, the first one was 3 times x squared plus 4 minus 2x squared all over 3 times the cube root of x squared plus 4, we said raised to the 4th power because squared is 4th power. Just do a little bit of cleaning up. What would that be? It would be 3x squared plus 12 minus 2x squared all over 3 times the cube root of x squared plus 4 raised to the 4th power. Let's just do a little bit of simplifying. How about that 3x squared with the 2x squared? We can just combine like terms, right? What are we left with? I'm going to go ahead and throw this in the answer blank because it's so close. 3x squared minus 2x squared would just be an x squared plus 12 all over 3 times the cube root of x squared plus 4 raised to the 4th power. Holy cow. So that problem was absolutely disgusting. Lots and lots of algebra there. But I want you to look at how hard was the actual calculus in that problem. We found the derivative of x, which was just 1. Then we used the power rule, which was just drop it, keep it, power minus 1, derivative of the inside. So really the only thing we found the derivative of there was the derivative of x squared plus 4. The rest of this is all simplification, bookkeeping, common denominators, making sure you understand your radicals and powers properly. So that's the type of problem that probably an A-level or B-level student would be able to get correct on the test. I'm not going to lie, without a lot of practice and a lot of algebraic skills, it's very difficult to make it through getting through the common denominator. Again, in the e-text, what they did is they simply factored out the x squared plus 4 to the negative 2/3. I don't know if that's easy to you. I don't know if you know how to factor out negative exponents. It can make it very, very difficult. I like seeing it as a denominator and then getting a common denominator. But either way, I'm going to give you credit if you do it the way they did in the book or you do it the way I did it. I don't care.